Hello everyone, welcome to the session on heat treatment process in module 3 of material science 18MA34 for third semester mechanical engineering students. So here in this particular session we are going to deal with two types of full heat treatment processes, that is normalizing and hardening. Okay, so in the previous session we have dealt regarding the details of different types of annealing, the concepts of recovery, recrystallization and grain growth, and prior to that we have understood the concept of the entire heat treatment and different formation of the temperature or relationship with respect to temperature and time. Okay, so now considering all those references, we are dealing with again two types here in this particular class. The first one being normalizing. See, normalizing and hardening both are again full heat treatment processes wherein we are going to consider the material combination at a particular temperature and we are going to hold the material for a particular duration of time, that is called as holding time, and at the end we are going to go with different types of cooling methods to bring the material to a particular microstructure to suit the particular purpose. Okay, so on this note we are going to take the normalizing. So here simultaneously we have to look upon both the graphical platform as well as the theoretical part here. So observe carefully. The heating steels to about 40 degrees Celsius to 50 degrees Celsius above the upper critical temperature, means to say that in this particular diagram you can observe, okay, this A3 line and ACM line are the lines that represents the upper critical temperatures of the material composition. Okay, so here this particular platform is already used to all of us by when we have dealt with the process of annealing here. So similarly, so this is the upper critical temperature line, that is A3 and ACM here. So according to the normalizing process, what we are supposed to do is that we are supposed to heat the material to a range of around 40 degrees Celsius to 50 degrees Celsius above the upper critical, means to say that from this particular, so basically it is 912 degrees Celsius. So from this particular you are going to heat it to a about 40 to 50 degrees Celsius above, means to say that above the upper critical temperature you are supposed to heat it to a range of 40 to 50 degrees Celsius. So this particular shaded portion represents the normalizing range in which the material is to be heated. Okay, then comes the concept of holding time. So holding time is the time defined wherein the entire microstructure of that particular material comes to a particular content. Okay, here we are supposed to concentrate on very short period of holding time, means to say that you are supposed to heat the material combination 40 to 50 degrees Celsius above the upper critical temperature, and within a very short span of time you are supposed to subject that particular material which is in normalizing range to cool down. So here we are going to opt for a process called as cooling through still air. So here still air cooling is a better cooling rate than the annealing process. So here one of the major purpose of opting for normalizing is that to give better properties in the materials rather than the annealing process. Okay, so here, so in case of annealing process, the heat treatment cycles is a very prolonged time, whereas in case of normalizing it has to be a very short period of time of consideration wherein the cooling rate is very high in case of normalizing. Hence we opt for cooling through still air. So this is the reason wherein normalizing will also be called by the name called as air quenching, still air. Okay, next comes the other parameters which are due to the normalizing effect or normalizing process. So here the type of structure will always be considered with respect to the thickness of the material which is considered in the normalizing process. Okay, so here what happens, thinner the specimen, the grain size will be very fine. So if the specimen is very thin, the grain size will be very fine. If the specimen is thick, then the grain size becomes thicker. So hence it is always better to opt for a very lesser thickness specimen so that it leads to better grain size in the structure. Then comes the major part, what is the microstructure in which the material will be subjected to. Okay, after going the normalizing process. After going the normalizing process, the material will be laid in the fine perlite structure in the microstructure. Okay, next comes the major purpose. The major purpose of opting the normalizing process is to provide harder and stronger steels than the annealed steels, that is the steels which have undergone the process of annealing. So you have to provide, if you have to provide the better, stronger and harder steels than the annealed steels, then we are going to opt for the normalizing process. So also with that, you will be going with certain improved machinability parameters in the material once the material is subjected to normalizing process. Okay, so this is something regarding normalizing. Keep in mind 40 to 50 degrees Celsius above upper critical temperature. So that leads to the normalizing temperature or the heating temperature. Hold it for a very short period of time and then cooling is done through still air. Okay, so next comes the concept of hardening. So the major intensity of going for hardening is to increase the hardness of that particular specimen. Okay, so here in this particular, again we are supposed to concentrate on those three parameters, that is heating temperature, holding time and cooling time. Okay, so here the heating temperature is different for two different types of steels, that is hypoeutectoid steel and hypereutectoid steel. So we'll go with the understanding of those two ranges now. For a hypoeutectoid steel, that means to say that the steel which consists of the carbon content less than 0.8% is called as hypoeutectoid steel, and the temperature range in which hypoeutectoid steel is to be considered is 30 to 50 degrees Celsius above the upper critical temperature. So just like in case of normalizing, here above the upper critical temperature, if you heat the material for 30 to 50 degrees Celsius, then it goes with the heating temperature for hypoeutectoid steel, that is steel which consists of less than 0.8% of carbon. Next comes the concept for the hypereutectoid steel, means to say that which consists greater than 0.8% of the carbon in the steel. So that there the temperature range differs. Here the concept goes like this, it is the 30 to 50 degrees Celsius above lower critical temperature. Okay, it is above lower critical temperature for hypereutectoid, and for hypoeutectoid it is above upper critical temperature. You can observe the same here. So this is the normalizing range here. So this is the upper critical temperature, A3 and ACM is the upper critical temperature line here, whereas A1 represents the lower critical temperature. So if you observe here, less than 0.8 is hypoeutectoid steel. For hypoeutectoid steel, the temperature is above upper critical temperature, that is 30 to 50 degrees Celsius of range above upper critical temperature. Whereas in case of hypereutectoid, that is greater than 0.8% of carbon, it is 30 to 50 degrees Celsius range above lower critical temperature to that of upper critical. So if you just observe here, this is the upper critical temperature, whereas the heating temperature going with above lower critical, that is above A1 temperature line here, that is you can observe here 750 to 780, that is 30 to 50 degrees Celsius above lower critical temperature. This is one particular difference when it comes to, okay, major difference when it comes to normalizing and hardening here. It differs with hypoeutectoid and hypereutectoid. So you have to be very clear when it comes to hardening, the temperature range to be heated is different for hypoeutectoid steel and hypereutectoid steel. For hypoeutectoid steel, it is above upper critical temperature. For hypereutectoid steel, it is above lower critical temperature. Okay, next comes the concept of holding time. So here in case of normalizing, you have held the entire specimen in the normalizing range for a very short period of time. Whereas in case of this particular process, it is hardening, you have to keep the specimen, okay, with the temperature to a particular consideration of hypoeutectoid or hypereutectoid range, okay, till the composition remains austenite, or still the composition austenite structure is produced. Okay, so that particular composition till the austenite structure is produced, this particular specimen or a material is to be held in that particular temperature range. Okay, then comes the cooling. So here in case of cooling, it is the quenching process. So quenching is nothing but sudden cooling. Okay, so here quenching is done by immersing the specimen, okay, which is in its austenite structure, by immersing it in water or oil. Okay, so here what happens, it is a sudden cooling process that results in the formation of the hardest structure in the iron carbon system, that is martensite. So when we opt for the process of quenching in water or oil, that leads to a cooling rate which is faster than the critical cooling rate. So critical cooling rate is what we have studied at the first class of the heat treatment process itself here. Okay, so if the cooling is faster than the critical cooling, then obviously we know that the structure will definitely be the martensite. So martensite is the hardest structure, or which do possess very high hardness factor when it comes to the different types of microstructures here in iron carbon system. So thereby what happens, if you opt for quenching in water, that is by immersing the specimen in water or oil bath, that leads to the development of a structure from austenite to martensite. So end of the time, the hardening process results in the development of microstructure that is called as martensite, whereas in case of normalizing it is fine perlite, whereas in case of hardening it is martensite, which is the hardest phase of iron carbon structure. So the major purpose, as it is said, to increase the hardness of the material, and the process of increasing the hardness is called as hardening. Okay, so this is something regarding hardening. So you can observe both the representation here. So we have to be very clear when it comes to hardening. It is hypoeutectoid steel which is above upper critical temperature. If it is hypereutectoid steel, it is above lower critical temperature. The range remains same, 30 to 50 degrees Celsius. But for hypo and hyper, it is different with respect to critical temperature. Whereas in case of normalizing, it is 40 to 50 degrees Celsius above upper critical temperature. So in case of normalizing, it doesn't deal with any combinations like hypoeutectoid steel or hypereutectoid steel, but it remains constant for all the composition, all the combinations, such as maybe it is less than 0.8% of carbon or greater than 0.8% of carbon. But end of the day, the fine perlite is the microstructure what we obtain in case of normalizing, whereas in case of hardening, we are going to get martensite, which is the hardest phase of iron carbon content. Let us now study a simple concept called as hardenability, which is due to the process called as hardening. Okay, we have to study hardenability in two factors. One is its definition, another one being the factors that are affecting the concept of hardenability. So as the name itself suggests hardenability, we can address the hardenability considering two basic fundamentals. One is the hardness, another one being the ability. So hardness is nothing but the resistance to plastic deformation. That is what we have studied in the previous classes. But hardenability becomes one among the ability of the material to get hardened as a result of hardening heat treatment process. So we have studied the process of hardening for different composition here. One is with respect to hypoeutectoid steel, another one is being hypereutectoid steel. So we have a temperature range for different types of steel composition here, and we are going to keep the temperature range by 30 to 50 degrees Celsius above upper critical temperature for hypoeutectoid steel and above lower critical temperature for hypereutectoid steel. But the holding time is same for both the composition of steel here, because we want to have complete austenitic structure in the microstructure of the iron carbon content here. So thereby what we do, we are going to keep the material at that particular temperature range, for hypoeutectoid as well as hypereutectoid respectively, till the structure becomes austenite. Once it becomes austenite, then what we are going to do is, we are going to introduce the cooling process called as quenching. So that quenching leads to the increase in the hardness of material, because quenching leads to the conversion of material which was in its austenitic stage to the martensite stage of microstructure. So the martensite phase is the strongest phase in the iron carbon composition. Okay, so in other words, the hardenability can also be considered like this. It is a measure of depth to which a specific alloy may be hardened upon quenching. So since quenching is the resultant that leads to the increase in the hardness of material, to what extent you can increase the hardenability or hardness of the material will also become a parameter to be considered. So that is where we are going to understand one more definition of hardenability, that it is to what depth the hardness can be introduced or increased in the material. So that particular definition or the statement will be justified once we go with the consideration of different factors that are affecting the concept called as hardenability. Okay, the first one being composition of steel and its manufacturing method. See, since the hardness is considered with respect to hypoeutectoid and hypereutectoid separately, so here composition of steel also becomes a vital parameter to identify or deal with the concept of hardness, since we do have different temperature, different consideration for hypoeutectoid and hypereutectoid. Then obviously the factor of hardness or increase in the hardness of material will definitely be differed when it comes to the hypoeutectoid and hypereutectoid. Hence composition of steel becomes one parameter that leads to the understanding or that affects the concept of hardenability. Next comes its manufacturing method. See, we have different processing methods to consider a material in its composition. Since composition is a vital part of any heat treatment process, so we do have definite methods to bring material in its particular composition. As in case here also, when it comes to hardenability, whatever the way we are going to consider the composition of steel, okay, into picture leads to the same parameter called as manufacturing method. That is nothing but the composition of steel and to what methods we have adopted to keep the specimen in that particular composition becomes one factor that leads to the hardenability concept. Next comes the quenching medium and method of quenching. See here, as we have stated in the cooling method, so it is quenching medium. Quenching medium is water or oil. So water and oil are the two mediums that can be accountable here for quenching. Then comes the method of quenching. See, method of quenching is again of two types. One method is completely immersing the material in water or oil. Okay, so you are going to consider a material which is in its austenitic structure to completely get dipped into the water bath or oil bath, so that the complete structure of the material from austenite gets converted to martensite, leading to complete hardness or introducing of or increasing the complete hardness in the material is one type of quenching medium. The another type is that you are going to consider the material in its austenitic stage and then you are going to start feeding a jet of water from one end, and over a period of time you are going to identify the depth to which the hardness is being increased in the specimen. So that is what we have considered in this particular statement. Okay, it is the measure of depth to which a specific alloy may be hardened upon quenching. Simple example to justify this statement goes with Jomini end quench tests. Okay, it is based on the person named Jomini here. Here there are particular standards that replicates the concepts of the measuring the depth of hardness here. Okay, this is the specimen here. The specimen should be given with a standard dimension of 100 millimeter length and 25 millimeter diameter. Okay, so it is to be 25 millimeter diameter and 100 millimeter length is the standard length of the specimen. This specimen will be held on a fixture here, and what we are going to do is that we are going to have a gap of 12.5 millimeter from the end of Jomini bar to that of inlet of the water jet. Okay, here the inlet of the water jet is at a distance of 12.5 millimeter from one end of the Jomini bar, and the diameter of opening for the water jet is 12.5 millimeter dia. Okay, so thereby the water which is coming from the water jet which is hitting the Jomini bar on one end will be at 24 degree Celsius. Okay, so this is the standard dimension for Jomini end quench test. So now what happened? You are going to consider this Jomini bar in the austenitic phase, means to say that this Jomini bar will be heated to a particular temperature so that the entire microstructure of the Jomini bar is in its austenitic stage. Now what you have to do? You have to convert that austenitic stage into martensite. So thereby what we do is you are going to take the Jomini bar which is in its austenitic temperature range and you are going to fix it to the fixture here, and from the distance of 12.5 millimeter with a water jet having the diameter of opening 12.5 millimeter, you are going to spray the water jet onto the Jomini bar on one of its end at 24 degrees Celsius. That is, water is coming at 24 degrees Celsius hitting the Jomini bar. Over a period of time, okay, over a period of time, this process of hitting the water jet onto the Gemini bar leads to quenching from one end to another end. Okay, thereby this results one more method of quenching, wherein to a particular depth you are going to increase the hardness, and to an extent the depth of that particular hardness will be measured, and that is called as hardenability. So this becomes the second method of quenching. The first method being completely immersing the material in its austenitic temperature to a water or to oil bath, so that at the end you will get the specimen in its martensite structure. In the second method is from one of the end you are going to start the quenching process, so that to a particular depth you can achieve the martensitic structure in the material, and remaining becomes non-martensite, or remaining becomes almost approaching martensite structure. Okay, the last parameter that affects the hardenability is thickness of the steel specimen. As we are aware of these particular parameters like thickness and the grain size and grain boundary, finer the thickness, better the grain size is what we have understood. So here again, if the thickness of specimen is very less, then the hardenability parameter could be achieved very fast. Means to say that the hardness can be achieved very fast. So this is the topic on the normalizing, hardening, hardenability and factors affecting hardenability. Thank you.